Hello. There are two different kinds of infrared cameras that you could possibly come across, and we would like to explain the differences between the two and the advantages and disadvantages. There are two different types of detectors that work inside the camera, and they have very distinct features and performances. There are photon quantum detectors, often also called cooled detectors, or the cameras are then called cooled cameras. The way these work is the actual detector surface on each pixel is a semiconductor material. Think of this as one pixel. So if you have a camera with 640 by 480 or 512 pixels, then you have that number of individual sensors in that camera. Each pixel or each sensor pixel will give you one separate temperature reading. So the way these work is you have the infrared radiation reaching the sensor surface through the optical system, and there's a photovoltaic effect associated with these that results in an electrical signal that can then be easily converted to a temperature with the help of the calibration curves. The specific requirement for this type of sensor is that the sensors have to be cooled down to somewhere between 70 and 80 Kelvin, so pretty cool. And that's done with integrated Stirling coolers. In the old days, you would have to you'd have to add liquid nitrogen to cool these sensors down. Today, they're all self-contained. All you have to do is plug them in, leave them running for a few minutes to cool down the sensor, and you're ready to go. On the other hand, again, think of this as one pixel. We have thermal detectors, or also called microbolometers, sometimes called uncooled cameras or uncooled sensors. The way these work is the actual pixel surface is an infrared absorbing material. So depending on the amount of radiation reaching the sensor surface, this material will heat up more or less. To get to the temperature measurement, then you have to actually measure the temperature of this surface. That's done with temperature-dependent resistance. So they can change the resistance, either go up or down, depending on the temperature change. And what we have to do then is determine the resistance. That's done by running a tiny bit of current through them to get a voltage drop, which gives you the electrical signal, again, with the help of calibration curves, turned into a temperature measurement. The part that's important to understand is reading these, running a little bit of current through them, will actually change the temperature of the surface. So these have to be operated in a very, very well-controlled thermal equilibrium or steady state, let's say. And that has very specific impact on the performance. On this slide, you can see what these detectors and cameras can look like. This would be a cooled camera. The detector is around about here. It's hermetically sealed behind a cold shield, and there's a Stirling cooler to cool down the sensor. On the other side, the microbolometers look much more like a sensor you would expect in a digital camera. The two basic and very, very, very important differences are these take snapshots. All pixels are fired at the same time, versus the microbolometers acquire images in a line-by-line fashion, which results, if you have moving objects, results in that rolling shutter effect. That's the main distinction, number one. The number two is these here have exposure times that can be controlled from very short to much longer, depending on the amount of radiation you're trying to capture. Only with infrared cameras, exposure time is called integration time. So this IT here stands for integration time. So that can go from the microsecond range down or up to the millisecond range. Versus the microbolometers, because of the steady state conditions they have to run in, they have a very limited frame rate. Typically, standard would be 30 frames per second, and you can go up to 50 or 60 frames per second. Everything beyond that is a different story. And the reason they need these, or they can only work with these lower frame rates, is consider again, this is a graph showing one pixel that's initially at a higher temperature. So the object it's looking at that's imaged onto that pixel is at a higher temperature. Or let's say that object moves or something changes rapidly in the image, and the next instant there's a much lower temperature that pixel is focused on. The pixel itself, though, because it's heated up depending on the amount of radiation it received when that picture was taken, is still at a higher temperature. And to be ready for the next measurement, it has to cool down to a defined level. And this cool down time is roughly in the range of 20, 30 milliseconds. So this is about that's why the 30 frames per second is such a standard number for microbolometers, because that's the amount of frames you can take, assuming that the sensor is completely reset and ready to take the next image. This is a little animation that shows how that actually works. What we're looking at here is an infrared camera with the lens taken off. So the rectangle here is the actual naked sensor surface that we're looking at. And you can see that white line moving up and down. That's the line-by-line acquisition. It's a thermal image, so the white means it's a slightly higher temperature. So here you can see how it reads out one line after the next. And to show you what that would look like, the two different sensors would look like in a real comparison, you can see here on this side we have a cooled camera. So we have the snapshot function and we have a higher frame rate. So we get a much clearer image of the object. Both objects are the same. It's like a computer fan that's powered up and turning. With the microbolometer, we get this effect that's caused by the line-by-line acquisition, but also by these higher exposure time, integration time associated with the microbolometers. Okay, that was all the main differences between the two types of sensors. Thank you very much for watching.